Okay, we're looking at some critical numbers of some piecewise functions and absolute value functions. With piecewise functions, obviously it's pretty important that your function is continuous. If it's not continuous, then that would be considered a critical point, because when there's no continuity, then it's not differentiable. And also you want to figure out just within these two pieces if there's any times in which the function is derivative is not defined and or the derivative is equal to 0. So let's first just determine continuity. So let's just evaluate f of 0 at the upper piece and the lower piece and see if they're the same. So f of 0 of the top function is equal to 0, and f of 0 of the bottom function is equal to 4. So since f of 0 on the left-hand side is not equal to f of 0 on the right-hand side, x equals 0 is a critical, can't spell critical point. Now let's consider the derivative. So we'll just take the derivative of the piecewise function by differentiating each piece. So this is negative 2x for x is less than 0, negative 2x, and this is also negative 2x for x is greater than 0. We've already determined that at x equals 0, the function is not continuous, so we don't need to consider if it's differentiable at x equals 0, because we already know it's not, since it's not continuous there. F of 0 and f of 4 are not the same. F of 0 is 0 and f of 0 is 4 is not the same for the left and right hand values. So I really just want to know, is f prime of x equal to 0 for any points here? Well, both have the same derivative, so negative 2x equals 0, so therefore x equals 0. But since we've already determined that x equals 0 is a critical point because the function is not continuous at x equals 0, it's redundant to say that 0 is a critical value. So therefore, our only critical number of this piecewise function is equal to 0. So here we have the absolute value function. Absolute value function is really just a piecewise function in disguise. So I'm going to rewrite our function as a piecewise function. My left-hand function will be x, the negative of x minus 2 when x is less than 0, and x minus 2 when x is greater than or equal to 0. So therefore, we know that a absolute value function is continuous because it looks like a v, where this is 2, and it just bounces up like that. Clearly there's a point where it's not differentiable because the left-hand derivative is negative 1 and the right-hand derivative is positive 1. So let's just take the derivative of our piecewise function. So f prime of x is equal to negative 1 and positive 1 for x is less than 0 and x is greater than or equal to 0. So since the left-hand derivative is negative 1, which is not equal to 1, which equals the right-hand derivative, x equals 0 is a critical point of f of x, and the only one. Okay, so we have the absolute value of a parabola, x squared plus 4x minus 12, which is a little bit different. So let's take a look at the graph of that. Here's the graph of our parabola, x squared plus 4x minus 12, and just notice that it intersects the x-axis at, looks like this is, it's got to be negative 6, and this has got to be positive 2. I just factored that in my head. So this is negative 6, and this is positive 2. But the absolute value just says, take anything that's negative and make it positive. So in this case, this piece all the way up to negative 6 is already positive, so the absolute value is not going to change this. Likewise, this piece going to the right greater than 2 is also already positive, so it's not going to change that. So what is the absolute value function? The absolute value due to the parabola, it just takes this negative piece here and flips it over. Okay, so this is the part of the absolute value function that sign gets changed. So you take the opposite sign that you have here, so you negate this piece here in between negative 6 and 2, and it flips it over. So let's show that function. So this is actually the absolute value function. This is what it looks like. It looks like a w. So therefore we don't need this function anymore, so we can hide that. So here is our new function that we're looking at. Well, clearly we have some critical points. We have this one right here because it's a horizontal tangent would be right there. And it's also not going to be differentiable at negative 6 as well as 2 because the parabola got turned over or the opposite sign in between negative 6 and 2, flip the function over. So we want to write this absolute value function as a piecewise function. Well, what did we say about the two left and right hand pieces? This part of the parabola didn't change. This part of the parabola didn't change. We took the opposite sign of this middle piece here. Originally was going down, and we flipped it over. So therefore we want to negate this piece in between negative 6 and 2. So let's write it as a piecewise function. So we have three pieces. The parabola did not change for x is less than or equal to negative 6. Again, I factored this in my head, x plus 6, x minus 2. So x is negative 6 and x is 2 are our x-intercepts. So therefore that's when it changed from just being the regular parabola to the opposite one. So now I need to take the opposite of this. So I want to take the negative of x squared plus 4x minus 12. And that's going to be in between negative 6 and 2. And lastly, we said the right-hand side didn't change, so we don't need to take the opposite of that. And that was for x is bigger than or equal to 2. The reason that we have the open circle on these two pieces here is because when we plug in negative 6, we get 0. And you don't want to negate 0. That's kind of silly. So therefore we have open circles on negative 6 and positive 2 here because there's no such thing as negative 0. So now here's our three pieces of our absolute value function, and we want to determine whether or not it's continuous at those points, and if it's not continuous, that would be considered a critical point, and then consider the derivatives to see if there's any points in which any of these derivatives are equal to 0, and or is it are the left and right hand derivatives the same at these points at which the functions change, meaning at negative 6 and at positive 2. So let's first look at continuity. Well, we can just look at the graph and notice that it is continuous because we just saw that it was a parabola that got flipped over. So continuity is maintained, so therefore there's no critical values gained by discontinuities. So the second thing we need to do is consider f prime of x and look at to see if there's any times with the derivatives equal to 0, and or is there any times in which the left hand and right hand derivatives are not the same at these 2 points, negative 6 and 2. So the top two are going to have the same derivative, 2x plus 4. Excuse me, the top and the bottom one, excuse me. And then this middle one is just going to be the negative of 2x plus 4. So that's going to be for less than negative 6. Negative 6 is less than x is less than 2. And x is greater than or equal to 2. So f prime of negative 6 from the left-hand side is going to be this function here. So that's 2 times negative 6 plus 4. So that's negative 12 plus 4, which is negative 8. F prime of negative 6 from the right-hand side is going to be this function here, or that derivative there, negative 2 times negative 6 plus 4. Well, that's just going to be the negative of that, which is 8. So since the left-hand derivative at x equals negative 6 equals negative 8, and the right-hand derivative at x equals negative 6 equals positive 8, therefore x equals negative 6 is a critical number. Now let's look at the derivative at 2 from the left-hand side, which would be, left-hand would be this function here, so that'd be negative 2 times 2 plus 4. So that's going to be equal to negative 8. And the derivative at 2 on the right-hand side is just going to be 2 times 2 plus 4, which is equal to 8. So again, since the left-hand derivative at x equals 2, I'm just going to write this out. You don't need. And you can see the left-hand derivative at x equals 2 is negative 8. The right-hand derivative at x equals 2 is positive 8. Therefore, x equals 2 is a critical number. So here we got two critical numbers at 2 and at negative 6. Lastly, we want to consider when f prime of x is equal to 0. So I'm just going to scroll down a little bit here. Okay, so I just took the derivative and slid it down a little bit so we can work with it now. So now last thing we want to do is consider when f prime of x is equal to 0. So I'm going to set the first piece equal to 0, so 2x plus 4 equals 0. So solving that, I got x equals negative 2. Well, this piece here is not defined for x is equal to negative 2, so it's not a critical value of our function. Setting the middle piece equal to 0, dividing by negative 1, I get 2x plus 4 equals 0, and x equals negative 2. Since negative 2 is in the interval from negative 6 to 2, here is a critical value. And likewise, when I look at the last piece of my piecewise function, clearly this is going to be negative 2 again. However, it's not in this interval. So the only critical number we got out of this was negative 2. So our critical numbers that we got are x equals negative 6 and x equals 2 because the derivative was not defined at those points, and x equals negative 2 since f prime of negative 2 was equal to 0. One more function. This way we're going to look at a trig example. Okay, so here's finding our critical points of the absolute value of cosine of x. Let's just first do a review of what cosine of x looked like. So here is cosine of x, and we're going over the interval 0 to 2 pi. So therefore, I've reduced it just from 0 to 2 pi. So cosine of x starts at 1, and then hits the x-axis at pi over 2, and then at pi it goes down to negative 1, and then 3 pi over 2 is at 0, and then at 2 pi it's equal to 1. So that's the cosine of x, but we're looking for the absolute value of x, absolute value of cosine of x. So I'm going to show that hidden function there, and so there's our absolute value function. Let me slide that in. Whoa, that was ugly. So here's our absolute value function. So notice that this lower piece here got flipped up in between pi over 2 and 3 pi over 2. So we're going to want to negate our original function cosine between pi over 2 and 3 pi over 2, and then just leave cosine alone between 0 and pi over 2 and 3 pi over 2 and 2 pi. So let's get rid of this function here. We don't need this anymore, and I don't need the cosine x. And then also notice the only time in which the derivative is equal to 0 is going to be right here, which should be pi, because originally it was down here at the bottom, so now it's up here. So let's look at that. So let's break up our absolute value function into a piecewise function. So our function is defined as cosine of x stayed the same between 0 and pi over 2. And then we negated or flipped it up, changed the sign. All of those are the same between x and 3 pi over 2. And then our function remained the same, between 3 pi over 2 and 2 pi. So clearly there's continuity. You always want to check continuity when you're talking about a piecewise function. So we just want to look at differentiability at the endpoints of each piecewise piece, and then to see if there's any times in which the derivative is equal to 0. So my derivative is going to be equal to negative sine of x from 0 to 2 pi, pi over 2. Derivative of the next piece would be negative sine, so that would be sine of x between pi over 2 and 3 pi over 2. And the last one would be negative sine of x between 3 pi over 2 and 2 pi. So f prime of pi over 2 from the left-hand side is going to be negative sine of pi over 2, which is negative 1, and f prime of pi over 2 from the right-hand side is going to be the sine of pi over 2, where this is my left hand and this is my right hand. That is equal to 1. So since, let's just write this. So here's just our brief discussion. The left-hand derivative and the right-hand derivative are not the same at pi over 2, so therefore pi over 2 is a critical number. Let's now look at 3 pi over 2. So f prime of 3 pi over 2 from the left-hand side is going to be equal to the sine of 3 pi over 2, because that's this middle piece here, and that's equal to negative 1. And f prime of 3 pi over 2 on the right-hand side is going to be negative sine of 3 pi over 2, and that's going to be equal to negative 1, which is equal to 1. So therefore we have the same argument we're going to have here. So here's a brief discussion saying that the left-hand derivative is -1, the right-hand derivative is 1 at 3 pi over 2, then 3 pi over 2 is a critical number. So lastly, we just want to set the derivatives equal to 0. We already saw that the only time that's going to happen is at pi. So let's just take a look, setting each one of these three pieces equal to 0. So, sine of x. So I'm going to set the first piece equal to 0. The only time sine of x equals 0 is at 0, pi, and 2 pi, because I multiply both sides by -1. And likewise, if I take the middle function and set that equal to 0, the only time that's going to happen is at 0, pi, and 2 pi. So therefore, our critical values are going to be these three numbers here, as well as pi over 2 and 3 pi over 2, which can be shown by the graph because there's horizontal tangents at 0, pi, and 2 pi, and it's not differentiable at pi over 2 and 3 pi over 2. Okay, sorry that got broken up, but hopefully you can figure out that these two videos go together.